Why am I talking about one of Einstein's visit to Paris a century after that visit? It's a very important question before we start. During that visit, he was shown a glimpse of the right path for relativity. It was not the path he pioneered and stuck to. The rest is, of course, history, but that history needs to be discussed because we have forgotten that history. The history of physics is an important component of doing physics because one needs to trace the path by which one came to the present, especially if it becomes clear that inappropriate choices have been made in the past. After all, empirical evidence, logic, and history are our only means to go forward. However, the focus of this talk is physics, as discussed during the week-long visit of April 1922. I had written a paper on many aspects of this visit and its analysis, discussions, and so on. The theories of relativity and Bergson philosophy of duration and simultaneity during and after Einstein's 1922 visit to Paris. This is available in the archives. Now, this is a timeline of Einstein and relativity, just a few of the highlights. 1905, the special theory of relativity with Lorentz Transformation, time dilation, etc. The same year, he found the general relation between mass and energy. 1907, equivalence principle, defining relation between acceleration and gravitation, the starting point of the theory of gravity. 1911, he derived the deflection of light, gravitational redshift, gravitational time dilation, etc. Not in the full theory, a primitive version of it. 1915, he had the full theory of general theory of relativity, equations of gravitation and dynamics. 1916, several predictions, including prediction of gravitational waves. And Schwarzschild found the solution of gravitational field outside a massive body. 1918, Einstein himself found the cosmological solution with the static universe model. 1919, solar eclipse and the test of the gravitational bending of light. This was a high point in the progression. 1922, he got the Nobel Prize for 1921 for explaining the photoelectric effect and not for any of these advances which happened between 1905 and 1919 in relativity. Now, between 1914 and 1918, this history of Europe and the world was engulfed in the difficulties related to First World War, as you know. And we see that science has been still going on at some level, even in Europe. Now, the visit to Paris from March 10 to April 7th will be discussed in the context of all this. 1918 to 1921, there was good news and bad news for Einstein's academic career. Gravitational bending of light was verified during the 1919 solar eclipse, the mission taken up by Eddington. And it was global news, newspapers celebrated it, as you know, in all over the world. This is from New York Times, I think. So Einstein became a household name after this much advertised test. But there were also several difficulties with anti-Semitic attacks on relativity in Germany. He was expecting a Nobel Prize, in fact, pretty desperate for it personally, but he didn't get it in 1920, though the nominations were very strong. In fact, 1920 prize went to Charles Gale, who invented the wonder alloy called Invar with a near zero thermal expansion, special steel and nickel alloy. 1921 price was deferred. So he had some difficulties around that time. It is at that time he got this invitation from a friend, a dear friend, Paul Langevin, in Paris for a talk, for a series of lectures there. So it's Langevin's letter says, at his last meeting, the Assembly of Professors at the College of France decided at my proposal to invite you to give this year's series of missionary lectures held by a foreign scholar in Paris every year. So he also mentioned, I must impress upon you the following reason for a general sort. The interest of science wants a re-establishment of relations between German-speaking scholars and us, French-speaking ones, which has become very bad due to the World War politics, where Germany and France were on opposite sides. And Einstein's reply, when I received your kind letter of invitation, I felt great and pure joy. And now 1 week later, I hesitantly and sadly take up my pen because I cannot accept the invitation now, as much as I would personally have liked to. And he gives the reasons. I came to the conclusion that at this moment of political tension, my visit to Paris would have been more adverse than favorable consequences. My colleagues here are still being excluded from all international scientific activities, and they are of the opinion that our fellow French professionals are primarily to blame for this. Then he says, people here would perceive a trip by me to Paris at the moment as an act of betrayal and would take such offense that very unpleasant consequence could arise. So he decided not to visit. However, he accepted the visit just after 1 week. Again, there's a very special reason for it. He says, further reflection on the fortuitous conversation with Rathenau. This is a minister of the new Republic, Weimar Republic, and he was a foreign minister and who was a friend of Einstein. Rathenau led me to a persuasion that I should have accepted your invitation despite all the reservations mentioned in my letter. In the endeavor gradually to repair the harm from this war, but to not allow oneself to be confused by petty considerations. So he decided to go. He said, I declare myself willing to come if you have not already chosen another person. Anyway, that's how the visit happened. A full account of this visit is written by Charles Nordman, who was an astronomer physicist in Paris. It's available, English translation is available in the web. It was a much advertised visit of Einstein in all this context, both in France and Germany. It was also much criticized by the press. There was polarization. It was very heavily attended. It was all over full sessions, and public could not get enough seats to come in. It was regulated by passes by Langevin himself. You can see the crowd outside the Collège de France waiting to enter, almost like a movie show first day. Now, some of the prominent persons in the events in this discussion, I just wanted to name some of them. Paul Langevin, who was a well-known physicist and he was a host. Charles Nordman was Einstein's friend, also an admirer. Paul Painlevé, he is a mathematician and physicist, French minister, and later French prime minister also. very accomplished physicist and mathematical physicist. Jacques Hadamard, well-known name, celestial mechanics person, mathematician. George Sagnac, the inventor of the Sagnac interferometer, which I will come to later. Alfred Kastler, who was a student at that time, a Nobel Prize winner later for atomic physics, optical pumping. And Henri Bergson, very well-known philosopher and respected and admired by both scholars and public. Nobel Prize in 1937 for literature. Now, these talks were arranged by Langevin at the Collège de France and Sorbonne. Now, there is an academy in France, very reputed Academy of the Sciences, and one might wonder why the academy was not involved in any of this. In fact, there was a session arranged there, but Einstein cancelled that session because he got the news that there would be a mass boycott during his address, and he wanted to avoid that embarrassment. He didn't go. The topic of discussion at the Collège de France and at the Sorbonne, of course, physics, mathematics, geometry, and philosophy, consequence of general theory of relativity, and much of the discussions were around the notion of time in relativity, the twin paradox, time and simultaneity, and so on. Also the philosophy of Kant and Ernst Mach was discussed in many occasions. Also, there were incidents where direct attacks on the theory of special relativity happened. One by George Sagnac, which I will talk about, and another person called Edward Gale. You will notice that this is the same name, Gale, which I mentioned earlier, Charles Edward Gale, who was the Nobel Prize winner for the inventor of INVAR. This Gale is a cousin of that Gale. One should not, some others confuse between the two personalities. Then there's a lasting controversy, which is lasting to this day. This is a Bergson-Einstein affair, about which much has been written about. There was a 15-minute debate which happened, which became very, very important later. Now, Einstein gave expository lectures in Collège de France, summarizing the theories of relativity along the lines of his well-known monograph, The Meaning of Relativity, which everybody would have seen. Now, though most of the discussion was centered around special theory of relativity, the new and strange aspects of the gravitational fields were discussed in some detail. So let me quickly say what that was. If you look at the Schwarzschild solution for the gravitational metric outside a spherical mass, you know that it has peculiarities. Like right now we talk about black holes and so on, but at that time things were not very clear. The time coordinate is multiplied by a factor square root of 1 minus 2 gm by rc square, where r is a radius and m is a mass of the object. And distance is divided by the similar kind of a quantity. Now, as you notice, if is 2 gm by c square r becomes close to 1, then the time stops and the distances, that part goes to infinity. So all the people, mathematical physicists, were very worried about this situation. So Hadamard asked, if the denominator of that term becomes null, meaning if this term becomes infinite, the formula no longer makes sense, or at least one could demand what is its physical meaning. So people thought the theory could become invalid and if such things happen in nature. And Einstein did not hide the fact that this profound question is somewhat embarrassing to him. If this term could effectively become null somewhere in the universe, then it would be an unimaginable disaster for a theory. And it's very difficult to say a priori what would occur physically because the formula ceases to apply. This is catastrophe, which Einstein pleasantly called the Hadamard catastrophe. Possible, and in this case, what would be its physical effects? So this was discussed, and people could not come to a conclusion. Even now, you can see that black hole solutions are somewhat of a conceptual difficulty in gravitational physics. Now, there was a direct attack on special relativity, as I mentioned. This Edward Guillaume was a Swiss physicist, but even more interestingly, he was Einstein's colleague in the patent office. He was a patent examiner like Einstein for several years. They were colleagues, and he had opinions about physics. He knew physics well, and so he has, in the previous days of the visit, in the April visit, most newspapers had published a wire announcing that Mr. Guillaume, a Swiss physicist, had discovered blatant calculating mistakes in Einstein's theory, and that he intended to reveal them before the public at the Collège de France. He has been communicating with Einstein before that, back and forth, and Einstein did not agree with his objections. Now he has come all the way to Paris to expose Einstein. It's a very strange incident, I would say. There's a newspaper report after the fact here. It doesn't say the full report, I don't have. But from the record of Nordman, it says he went up the stage and he had an opportunity to talk there. But after a few moments, it became clear to everyone that this was not going to be the day, nor the individual that would force Einstein to bite the dust. Nobody could understand anything, and nobody took it seriously. But there was another attack, which was very, very important, which was of a different kind, which is what I want to talk now. It's some remarks made by this person called George Sagnac. The name is very familiar to you. Kassler, who was a student, then writes about it from the unforgettable memory of those sessions. Allow me to recall a memory from youth when Paul Langevin had the bold idea to invite Einstein in Paris. The understanding at that time was not without risk, because undertaking was not without risk, because Einstein was then a professor in Berlin and any German demonstrations could be feared. However, all went fine. Einstein started to give a talk for a general audience about relativity, which we just mentioned. Then he said, there were dramatic moments too. For instance, when old Sagnac, the inventor of the ingenious interferometer, gave vent to his anger against the theory of relativity, on which he put all the blame. The only way was to let that storm die down. Now, Sagnac was a well-known experimental researcher. He published a paper in 1930, more than two papers actually, in the title, the English translation, regarding the proof for the existence of a luminiferous ether using a rotating interferometer experiment, in which he claimed that his experiment shows the existence of the ether and the Galilean nature of the velocity of the light in this rotating interference experiment. And he described this interferometer in detail in a sketch in this paper and so on. Now, as you know, this is the interferometer which we now call the Sagnac interferometer or an optical gyroscope. The most precise way of measuring rotations is still this cutting kind of an instrument. This is a laser interferometer here, but you can active or passive, you can make this rotating interferometers. Now, Sagnac logic was very, very simple. Suppose you have a particular length over which propagation of light happens. You want to measure the velocity. The only way is to measure the length and measure the time duration and take the ratio, you get the velocity. Now you need 2 clocks for doing that. It can be done. But suppose that the velocity is not an invariant but Galilean, C minus V. Now, if it is a constant, of course, you don't bother whether the frame is moving or not. But if it is not, then it becomes very important whether the frame is moving at some velocity V, like that. And then if you want to measure the velocity, you need to measure, length measurement is not an issue, but the time measurement needs these 2 clocks. And if you are at one point here, you don't know what the time on the other clock is, unless you bring back that information by propagating something back. So there is no way of knowing the time of a clock which is far away, which is really the cardinal point of all issues of relativity. Now, assuming that the velocity is c minus v, you can see that the time duration will be more, because L by c is the time duration to go from here to there. Now, by the time light reaches from one end to other end, the frame has moved extra distance, and you have to add that extra time delay, and you get this extra time delay VL by c square. And this is a thing, but you don't know where it is because of the clocks or because of the propagation. The two cannot be distinguished. The two cannot be separated. And Sagnac had the brilliant idea that you don't need to use the 2 clocks. You could have done that same experiment by bending this particular device, bending around, making a loop like this. If you do that, then as the light propagates in the circle and it comes back to the same point in the circle, there is only need for 1 clock. That was a logic essentially, but this is not the way he presented it. He had a theory, a separate theory, because of which he thought this way. Anyway, the Sagnac interferometer or the optical gyroscope today is just a very simple device like this, which can rotate and tell you what the rotation rate is. Now, behind all this, you can see that the question is, how does light propagate in nature? And Einstein said there is invariance of the relative speed of light in all inertial frames. Look at what Charles Nordman write in 1922 in the report of Einstein physics. He says, Einstein's theory is very good. However, there is still something infinitely troubling in the Einsteinian system. This system is admirably coherent, but rests on a particular conception of the propagation of light. How are we to imagine that the propagation of a ray of light could be identical to an observer who flies away from it and for an observer who rushes towards to meet it? If this is possible, it is in any case inconceivable to our customary mentality. And no matter how hard we try, we cannot make the mechanism and nature of that propagation intelligible. It must be confessed that here lies a mystery which eludes us. The whole Einsteinian synthesis, as coherent as it is, rests on a mystery exactly like the revealed religions. This is an admirer of Einstein writing about it. Now, this is exactly what Sagnac was attacking. But what happened? There is a record from some other person who attended some of these lectures, J.P. Pomey, a physicist and a writer. He says about the Sagnac incident, what was the attitude there? Did one acclaim the Frenchman? No. At first, it was a scandal because of the violence of the intervention. Apparently, Sagnac was very agitated. Mr. Einstein was quite disconcerted. Perhaps he expected a fight on political grounds, but this brutal attack on scientific grounds flustered him. Fortunately, he was made to understand that the best was to reply nothing. At any rate, Mr. Sagnac spoke very fast. At any rate, his address sounded like a manifesto, for he did not do what was needed to make him understood, unfortunately. I suppose he saw himself as facing irreducible adversaries. Anyway, it says, the attendants let the storm pass, and when he at last took his seat, the discussion started again as if his communication had never happened. But that outburst was totally unfit to induce any exchange of useful observations. So that is what happened. Unfortunate for Sagnac, because several years, 3 years later, Michelson published a paper in Astrophysical Journal, April 1935. It says, the effect of Earth's rotation on the velocity of light. This is the same Michelson who did the Michelson-Morley experiment. It says the theory of the effect of the rotation of the Earth on the velocity of light was derived on the hypothesis of a fixed ether. In fact, he says this was already done in 1905, but the experiment could be done only later. So Michelson here talks about an experiment to detect the velocity, the change in the velocity of light in a rotating frame, assuming the hypothesis of a fixed ether. And the same journal, same year, he published this result of the experiment. It's a heroic experiment because he had to use a evacuated interferometer 1 mile in length, in arm length. It is on the scale of the same scale as the gravitational wave detectors of today, more than a kilometer sized interferometer, which he operated in 1925. There was no laser and all that, a very difficult experiment, but he did the experiment. This is the result of the experiment. What was the result? He found that the velocity of light is retarded in the direction of the rotation. It says the beam traversing the rectangle in the counterclockwise direction was retarded. The observed displacement of the fringes was found to be 0.23, agreeing with the computed value 0.236 within the limits of experimental error. Of course, nobody talks about these kind of experiments. People are probably, even people who teach and learn special relativity and so on, are probably not even aware of these important experiments. I don't want to talk about more about this, but I wanted to set this history in the right context. Unfortunately for Sagnac, there was no discussion of all this together later. Now, again, going back to the discussions, another point from Alfred Kassler, and there were difficult moments too, when great mathematician Paul Panlevé, talking about the adventure of the two friends, the one who stayed in a place and the one who left by train and came back. You know, this is about the twin paradox. There were a lot of heated discussions, heated but friendly discussions during Einstein's 1 week visit, because this was the same point on which he was criticized heavily in Germany by several people before that. And Kassel says, Panlevé refused obstinately to understand why the latter had remained younger than the first one. So let's go back to that, because Einstein had an answer. Einstein had an answer in that debate, and Einstein had an answer before that in print. So I want to mention both. It was Langevin himself who introduced the twin paradox, and that too in a conference on philosophy in Bologna in 1911. And many philosophers were jolted into a discussion about the multitude of times in the physical world, one each and one's own for every inertial observer. So Langevin in that talk, he said, for this, it is sufficient that our traveler consents to be locked in a projectile that would be launched from Earth with a velocity sufficiently close to that of light. Return to Earth, he has aged 2 years. Then he leaves his arc and finds that the world has 200 years older. If his velocity remained in the range of only 1/20,000 less than the velocity of light. And he also made an arbitrary statement, which is not part of special relativity. One who has aged the least is the one who had suffered the greatest accelerations. Now, we all know that a clock that moves relatively ages more slowly. Time dilation in theories of relativity is well known. Clocks in Einstein's special relativity says if a clock is taken and passed around and brought back after some transport, it will have time dilation. And this is a formula which is given. The formula, the clock at the which remained at rest and related to the clock which is traveled is by this particular formula. So there is time dilation because the time in this clock is reduced by this particular factor. Now this dt can be divided into small sections in a differential sense, and they can be all added up or integrated to get the final time dilation. So the simplest conclusion is that every transporter clock runs slower. That's a very definitive conclusion in special relativity. Transporter clocks always run slower. But the problem in relativity, special relativity, is it's a symmetric theory. How do you decide which is a transporter clock? Because from the reference frame of one clock, the other clock is relatively moving. But when you change the frame, it is reciprocal. And in 1922, nothing was known experimentally about time dilation. One should keep in mind that now it is very easy to talk about these things pointing to experiments, but in 1922, nothing was known experimentally about time dilation. Now the first paper probably on time dilation was about Homi Bhabha. This is a paper, his paper on what he called the U particle, which he wanted to identify with what was called the heavy electrons in those days. Now we know these U particles are mu mesons. So this is a paper of Homi Bhabha in Nature 1937 on nuclear forces, heavy electrons and beta decay, where he publishes a theory in analogy with Yukawa's theory, which he says these particles will disintegrate into a positive electron and a neutrino. This disintegration being spontaneous, the U particle may be described as a clock, and hence it follows merely from considerations of relativity. The time of disintegration is longer when the particle is in motion. We believe that this may have to do with the fact observed by Blackett and others that below 2×10⁸ electron volts, most cosmic ray particles are electrons. Above this energy, they are heavy electrons, and very clear. But the experiment was done by Rossi and Hall later, few years later, where they were not aware of Bhabha's paper on mu mesons. Now, in relativity, the twin paradox is known to everybody. The problem is it's a symmetric theory. So if you have two clocks, and if one clock is moving relatively and it is brought back, you will think that that clock has time dilation. But relative to the other clock, it is this clock which goes and comes back kinematically. So it is this clock which should have the time dilation relative to the other clock. So this is a completely symmetric situation in special relativity. That's a problem. Since it's a symmetric reciprocal situation, how do you decide which clock runs slower? If you draw a space-time diagram for each of the situation, in the frame of the first clock, the other clock goes through a particular trajectory and comes back. But equally truly, in the frame of the other clock, you have exactly reciprocal diagram with the motion of the clock reversed. The only difference is possibly that in one frame, for a brief moment, there is a force you can experience because of the acceleration. Otherwise, the space-time diagrams are completely identical. From the space-time diagrams, you cannot determine which clock is running slower, contrary to everything which is said in textbook. In fact, almost all discussions and textbooks dismiss this paradox and make the statement that the problem is solved within the special theory of relativity alone. Teachers teach this claim, which they cannot prove, to generations of students, unfortunately. However, why am I saying this? We can look at what was Einstein's own resolution of twin paradoxes. This is not what is discussed in textbook. Einstein must have had a view on twin paradox, right? So he was forced to talk about his solution of twin paradox in these debates. And there's a history to it. Einstein had published a paper in 1980 about twin paradox. That's the only thing he wrote about twin paradox. It was written in the form of a dialogue. It says dialogue about objections to the theory of relativity. English translation here goes like this. It's about a critic confronting a relativist. He says, people like me have quite often expressed their various doubts about the theory of relativity in journals, but rarely has one of your relativists responded. Einstein is writing this paper in a self-critical manner. So he says, rarely one of you relativists has responded. And he also says, I've come to you personally in order to make it impossible for you to shirk it as it has happened before. So Einstein was well aware that he did not answer the criticisms. What was his resolution? His published resolution rejects all the resolutions you see in most textbooks on special relativity. Einstein admitted that the special theory of relativity time dilation is symmetric between the two clocks. Then he used the gravitational time dilation in general theory of relativity to suggest a solution. So he said special relativity is not enough. You need general theory of relativity to solve this problem. Though he didn't calculate the solution in that particular paper, this is a solution he suggested. I have written a paper about this, analyzing what his solution was, doing a calculation about it and so on in current science in the centenary year. You can go back and look at it. I don't want to go into details of the solution. What I wanted to notice here was, it was amusing for me to note that Einstein chose not to mention the gravitational resolution in the debates in Paris, possibly fearing that people will interpret it as the correctness of the anti-relativity campaign which was going on in Germany, because there he was trying to say that special relativity was enough in the early days. So there is an interesting incident here. I not studied it further. Now, another main point we wanted to discuss today about time and simultaneity. There's a lasting controversy, and that's why I talked about the echoes, which you can hear even today. A discussion was arranged by the French Philosophical Society at the Sorbonne University. This was a day before the visit ended. And in the introduction to that session, the president of the society, French Philosophical Society, introduced. He said, during the 4th International Congress in Bologna, Langevin revealed the mysteries of the restricted theory, special theory of relativity, to astonished but singularly captivated philosophers. In October, as an apostle of new evangel, he expounded again, under a slightly different form, the discoveries of Mr. Einstein in front of the members of the French Society of Philosophy. And at some stage in the discussion, a lot of things were discussed, including Kantian philosophy, Machian philosophy, various other aspects, role of geometry, mathematics in physics, and so on. At some stage in the discussion, Henri Bergson, who was present there, was requested to speak about his opinion about time. And Bergson said, "I came here to listen. I did not intend to speak, but I will yield to the kind insistence of the Society of Philosophy." Now, Bergson was also a speaker in the Bologna conference we mentioned, 1911. But he was talking about philosophy there on philosophical intuition. He was the top philosopher of those times. Now, the 1922 visit attracted the attention of historians because of short discussion between Einstein and Henri Bergson in the discussion session at the Sorbonne. He was a professor of philosophy at the College of France. As I said, he was Nobel Prize for Literature in 1937. He wrote a book called Duration and Simultaneity with reference to Einstein's theory in 1922 itself. So he was studying time in relativity. And Bergson commented briefly on Einstein's theory during this session. And he had criticisms to make. And the criticisms became, it had some role to play. Probably it had, one even speculates sometimes that the criticism seems to imply severe personal consequence for Einstein. What happened was, if you check the 1921 Nobel Prize presentation speech by Arrhenius, which was given in 1922 December, says, "There is probably no physicist living today whose name has become so widely known as that of Albert Einstein. Most discussion centers on his theory of relativity." Then he says, "It will be no secret that the famous philosopher Bergson in Paris has challenged his theory, while other philosophers have acclaimed it wholeheartedly." Then he says, third group of studies for which in particular Einstein has received the Nobel Prize falls within the domain of quantum theory founded by Planck, the photoelectric effect, and so on. So the criticisms, not only this, but various others had played a crucial role in why Einstein did not get a Nobel Prize for the discoveries in relativity. So Bergson's critique of Einstein's theory is the most discussed event of the visit by historians. A lot has been written. And if you are interested, one can look at this recent book, The Physicist and the Philosopher by Jimena Canales. It's a very recent book with a lot of details, maybe too many details. Now, Henri Bergson as a person, he was a top mathematics student as an undergraduate, but shifted and graduated in philosophy. He wrote many widely read monographs in philosophy of being in the physical world. A very deep work on time, duration, and simultaneity. You can see a list of several books, which is all available. Now, physical time and psychological intuition, psychological time. If you look in the 19th century, what was the picture of these? You can see that physical time was absolute and universal, identical for everybody. Notion of simultaneous occurrence of two or more events was also an absolute, in the sense it's the same for everybody, universal. There was intuitive mapping from physical time to individual's time with no conflict with common sense. There was no conflict between physics and common sense in 19th century. So Bergson says in 1922, common sense believes in a unique time, the same for all beings and all things. The idea of a universal time common to conscious being and to things is a simple hypothesis. Now, there is clash between the new physics of relativity and philosophy, obviously, because in early relativity, Lorentz relativity, either was a necessity, but which could not be detected, as Michelson's experiment showed. Thus, for the first time, physical time became a multitude of times. There was time dilation, which depends on velocity relative to ether. So it was different for different individuals moving at different speeds, depending on their speed. However, nobody could detect their motion relative to ether. So this was a severe problem for philosophy. Motion relative to ether cannot be detected, and Lorentz relativity has a multitude of real times based on real motion relative to one master frame. But if nobody could detect this motion, there is no way to map the motion and its time. And Bergson must have been relieved when Einstein's theory came and effaced the Lorentz-Poincare theory. Because in Einstein's theory, there is no preferred frame, there is no absolute frame. And the time dilation is a relative coordinate kinematical effect. Since Einstein's time dilation depends on relative motion and the speed of separation, not motion, it's speed of only separation, relative motion. It is symmetrical between two observers. Anybody can claim a state of rest, and then the other person is in motion. There is multitude of times, but they are all equivalent. So there is different time for different people, but they are all equivalent. Therefore, Bergson interpreted time in special relativity as mere mathematical type with kinematical multiplicity. Then the notion of absolute time and simultaneity are not affected in reality, because Bergson thought these times are not real. So at the session in Sorbonne, Bergson started his comments by expressing his admiration for Einstein's theory, which was new physics and in some respects, new way of thinking. Then he stated the issue of contention. Common sense believes in unique time, the same for all beings and all things, the idea of universal time, common to conscious beings and to things, the simple hypothesis. But it's a hypothesis that I believe to be founded on which in my opinion contains nothing incompatible with the theory of relativity. I cannot undertake to demonstrate this link. It would be necessary to take the terms which enter the Lorentz equation one by one and search for their concrete significance, which he does in his book. Then one would finally find that the multiple times the theory of relativity deals with are far from being able to pretend the same degree of reality. It's a severe criticism of special relativity. But all that I cannot establish as regards time in general, I seek your permission to do, or at least glimpse, for the specific case of simultaneity. Here we will see easily that the relativistic point of view does not exclude the intuitive point of view and even necessarily implies it. So he wanted to just find what extent this relativity renounces intuition and to what extent it remains attached to it. And Einstein was dismissive actually. He summarized what he thought were points raised by Bergson and concluded, the question is therefore the following: is the time of the philosopher the same as one of physicists? And finally answered, there is not a time for time of philosophers. There's only a psychological time, different from the time of the physicists. So let's look at this particular question of issue of simultaneity. I will talk about in a more detailed fashion next week in the NSF colloquium. But here I want to give just an intuitive idea. Einstein said in his book, Relativity, the Special and General Theory, he said, we require a definition of simultaneity such that this definition supplies us with the method by means of which one can decide by experiment whether or not both the lightning strokes occurred simultaneously. So there are two events happening, two lightning strokes at two different places, A and B. How do you decide whether they are simultaneous? And he had a particular example in this book, which is a popular physics book. Everybody would have seen this book. So he asked, are two events, example, two lightning strokes at A and B, which are simultaneous with reference to the railway embankment, also simultaneous related to the train. So he is considering a railway platform and a train which is moving relative to it. Two observers M and M prime at the midpoints of the platform and in the train, and they coincide at some particular point, which happened to be the time at which these two lightning strokes happen. The question is, if one of them sees simultaneously, what does the other observer perceive? The simple question, we should be able to answer that. Now, the question of deciding simultaneity is actually a very subtle question in the theory of relativity. For example, here there's an observer at the midpoint of a frame, which is a stationary frame. You know that it is stationary, it's a rest frame of the observer. And there are these clocks, and there are two events which happen at point A and point B. Then two light signals come to the person simultaneously. They arrive at the midpoint simultaneously. Can you decide whether these events happened also simultaneously? One would say yes, because we know there is a frame at rest. Similarly, if two light signals are sent from here outwards, can you decide whether they reach the endpoints at the same time if you are at the midpoint and if the frame is stationary? One would say yes, within the special theory of relativity, because the rest frame and the velocity of light is a constant in both directions. However, you realize that if the frame is moving, we cannot answer this question really unless we assume something about the propagation of light. In moving frame, simultaneously defined in terms of coincidence with a local clock depends on the assumption about the propagation of the messenger waves. It depends on the convention. For example, just look at the case of sound. Two alarm clocks are going off simultaneously. Somebody is at the midpoint, stationary. We know intuitively and from experiments that the sound will reach simultaneously at the observer. So simultaneously is very clear here. Whereas in the frame of a moving person, in the rest frame of a moving person, what happens? In the rest frame, the velocity of sound is more from one direction than from the other direction, because velocity of sound depends on the motion of the observer. So in such a case, one signal will reach first and then the other signal will reach. So there is no simultaneity. So we immediately see that for the case of sound, which is a Galilean wave, where the velocity is not a constant, if the events are simultaneous for one observer, they are not simultaneous for another moving observer. It's very clear. Therefore, so the point is the two distant events judged as simultaneous by one observer will be perceived as successive by another observer when the relative velocity of messenger waves is Galilean, like sound. However, if the velocity of the waves were an invariant constant, suppose the velocity of sound was also a constant, then this conclusion should change. Then two events which are simultaneous to one would have been simultaneous for the other also. Let's see that. So we can answer Einstein's question, are two events which are simultaneous with reference to the railway embankment also simultaneous relative to the train, assuming that the velocity of light is an invariant constant, because that is what Einstein assumed. To a person at the midpoint here, of course, the signals arrive simultaneously. But to a person who is moving also, the velocity from the one direction is exactly the same as the velocity from the other direction. This is a person in the rest frame. The sources are moving. In the rest frame of this person, the sources will move, but the velocity of light does not depend on the velocity of the source. So therefore, these two signals will again come simultaneously. So if the velocity of sound, if the velocity of light is invariant in all frames, simultaneity for one person is also simultaneity for another person. This is what Bergson was talking about. It's clear that the apparent relativity of simultaneity is a Galilean experience. Simultaneity is universal if the relative velocity of light is an invariant constant. But Einstein concluded in his book, which you can go back and read. It's very interesting. And it's ununderstandable why he concluded like this. He concluded, observers who take the railway train as a reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. We thus arrive at the important result. Events which are simultaneous with reference to the embankment are not simultaneous with respect to the train and vice versa. Relativity of simultaneity. So he inadvertently used Galilean light to arrive at this conclusion. He was analyzing the theory after assuming that the velocity of light was invariant, but during the analysis he forgot that and used Galilean light to make a conclusion. The relativity of simultaneity therefore is inconsistent with the invariant relative velocity of light. These two are inconsistent. Thus, a fatal error in the formulation of special relativity that renders the theory inconsistent was made by Einstein. Anybody can read his writing and verify this. This was what Henri Bergson pointed to in the discussion at Sorbonne and wrote about it in his book, Duration and Simultaneity, very, very clearly. Let's look at this passage. He says, he repeats Einstein's analysis of the train and platform example in detail in book, and then he says, this passage enables us to catch on the wing an ambiguity that has been the cause of a good many misunderstandings. We must not forget that the train and the track are in a state of reciprocal motion. They are in relative motion. As in special relativity, there is no absolute motion. Let us now emit our two flashes of lightning. The point from which they set out no more belongs to the ground than to the train. The waves advance independently of the motion of their source. That's a fundamental assumption in special relativity. It then becomes clear, it becomes evident at once the two systems are interchangeable and that exactly the same thing will occur at M prime as at the corresponding point M. If M is at the midpoint of AB platform, and if it is at M, we perceive simultaneity on the track. It is at M prime, the middle of B prime, A prime, which is the midpoint of the train. We shall perceive the same simultaneity in the train. What is simultaneity with respect to the track is simultaneity with respect to the train, which is what the conclusion we arrived at using simple high school logic. There is no complexity in that logic, which we already see, which is what Bergson was saying already in 1922. And contrast this with Einstein's incorrect deduction. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. We thus arrive at the important result, relativity of simultaneity. So there is a clear conflict here, and we already saw from a simple analysis that it is Bergson's conclusion. We also came to from simple logic. Bergson's logic was impeccable. However, many attacked Bergson on Einstein's behalf later in writing. Jean Becquerel, Andre Merz, and so on. Einstein himself ridiculed Bergson in private, but never wrote anything in reply directly. Yet it is known that Einstein got a copy of the book and read it. It's interesting. Anybody can read Einstein's Relativity, the Special and General Theory. It's a popular physics book. Or you can read his relativity paper itself and confirm Einstein's fatal error and Bergson's impeccable logical refutation. then the significance of these experimental observations of Sagnac and Michelson come to the fore, because those experiments also highlight the same point, that there is no the relative velocity of light being an invariant, and the fact that there is lack of universality and simultaneity, they are in conflict. Empirical evidence, logic, and history are our only means to go forward. We should never undermine them in favor of scriptures. So I want to end this talk with a quotation from Einstein himself. It says, "The theoretical scientific researcher is not to be envied, because nature, or more precisely put, experiment, is a merciless and not very kindly judge of his efforts. She never says yes to a theory, in the best case merely perhaps, but in most cases simply no. If an experiment agrees with the theory, it means perhaps. If it does not agree, then it means no. Every theory is sure to experience its no someday. Most theories already do so after their formulation. It's just that now it is a receiving time for Einstein's theory." I again point to this reference where some of these things are discussed. And I will discuss simultaneity, synchronization of atomic clocks, and so on from a thoroughly physics point of view next week again. Thank you very much.